How to conduct a water monitoring study. When starting your study, you'll need to identify the type of chemical or chemicals you want to monitor, such as metals, pharmaceuticals, personal care products, and pesticides. Identifying the potential source and discharge pattern of a chemical is an important step. For example, human pharmaceuticals will be continuously released, usually via the effluent of a wastewater treatment plant. On the other hand, a pesticide will run off from a treated field during periods of rainfall, so exposure will be more intermittent. This will help determine where you need to monitor and the frequency and duration of the monitoring. For the pharmaceutical example, monthly sampling over a year up and downstream of a wastewater treatment plant could be the best approach. Whereas in the pesticide example, continuous sampling alongside a treated field for a few weeks either side of the pesticide application window might be the best option. Once you've arrived on site, there are initial observations you may want to record. These could include a description of the location, whether there's any visible flooding, weather conditions and temperature, any evidence of spills. It may be beneficial to measure additional water properties including pH, turbidity, electrical conductivity, nutrient content and the flow. When you get back to your office, it's also worth noting other information for your monitoring area for the day of sampling, like amounts of rainfall or river flow volumes. These can often be obtained from online resources such as weather and environmental agency websites. When undertaking monitoring, you need to consider the most appropriate sampling method. Will you take grab samples at specific times and locations, or combine samples in one representative composite sample, or use passive samplers to determine an average concentration over a set period of time? If the chemicals of interest are sorptive, you may also want to consider taking sediment samples using a sediment grab or corer. Before heading out into the field, you must prepare all the equipment required for your chosen sampling method. Make sure to refer back to your risk assessment and health and safety documents and bring spare equipment if required. It can be a good idea to prepare a checklist and protocol to ensure sampling is carried out consistently. Wet wipes, tissue paper and a bin liner for waste are always useful as sampling can be messy. Take a field notebook to record any observations you make. A mobile phone or camera can also be useful for obtaining photographs of the site at the time of sampling. Ensure you're wearing all the required PPE and all sampling bottles are correctly labelled with the time, date and location. Buckets and sampling bottles need to be rinsed with the water from the water body prior to collecting your sample. This is called conditioning your sampling equipment and must be repeated at each sampling location. Using a bucket for collecting samples is ideal for scenarios where you can access the middle of the water body via a bridge or boat. This ensures your sample is more representative of the wider water body and can reduce disturbance of the sediment, which may contaminate your sample. Make sure your bucket is tightly tied to your rope, then slowly lower over the side of the bridge or boat until it's under the water surface. Once the bucket is full, slowly pull up and collect your sample. Alternatively, you may want to use a beaker on a stick. While not ideal, this method can be used to take samples from the bank if you're unable to access the center of the water body. Once collected, you may need to filter the water with a syringe filter if it contains suspended material such as sediment, leaves or other debris, or depending on the analysis you have planned. If freezing samples, make sure to leave room in sample bottles to allow for the expansion of water as it freezes. Grab samples are a cheap option if your budget is limited. They're quick and you don't need extensive training or specific skills to use equipment. However, samples may not be as spatially or temporally representative as they will be taken at one specific time and place. For example, with an intermittent discharge scenario, you may not capture the chemical pollution event. There are also a suite of in-situ measurements that can be undertaken. The best option is to use a multi-parameter sonde that provides information on things like the pH, conductivity, temperature, dissolved oxygen concentration, and turbidity of the water at the sampling location. Simple test strips can also be used. While less accurate than a sonde, a range of strips are available that provide information on things like pH and metal, nitrate and ammonia concentrations of a water sample. Dip the strip into your collected sample, then wait for the appropriate time before comparing the color of your strip to the color key on the packaging. Turbidity could also be measured, if appropriate, using a simple method such as the Secchi disc method or the opal scale. An alternative method, depending on budget and access, is an autosampler, which allows you to take samples at high regularity. This approach is more likely to catch peaks of exposure. To use an automatic sampler, you must first connect it to a power supply or battery. Set the sampler to take the correct volume of samples at the times you desire, ensuring you have enough spare bottles. The time and date of your sample will be automatically recorded. An automatic sampler can also be used to collect composite samples. If sampling over a long period of time, check the equipment is working correctly and regularly maintained. Passive samplers, such as chemcatchers or POSIS, provide you with an average concentration of a chemical over time. Like autosamplers, they're a good option where concentrations of a chemical vary significantly over time. When using a passive sampler, you must first choose a suitable place to leave the sampler to prevent theft and human or environmental disturbances. Depending on the contaminant being studied, a suitable receiving phase disc should be chosen. Place the sampler in the water body, attached securely and protected from debris or from being swept away, ensuring it's placed somewhere it will remain submerged. Once the collection period is over, remove the sampler from the water carefully. Dismantle, remove the sample disc, then place it into labelled sampling containers. The benefits of this method is its ability to detect contamination events potentially missed by grab sampling, and no power source is required. However, the samplers may be disturbed or stolen, can be difficult to set up, and do not provide time-specific data. For some contaminants, you may want to collect both water and sediment samples. Make sure you collect the water sample first to avoid suspending material in the water column and influencing the water samples. You can either collect your sediment sample using a spade, sediment grab sampler, or a sediment corer, making sure your equipment is clean before you start. When using the spade, first ensure it's safe to enter the water body, then shovel sediment into a bucket and safely walk back to the bank. Divide the sediment into the smaller sampling containers, avoiding collecting excess water. A grab sediment sampler can be used for larger or deeper water bodies where access is via boat or bridge. A corer allows you to sample and analyze sediments at different depths and can be useful in constructing a history of chemical contamination at a site. After collecting samples, always clean the equipment using deionized water, then dry it off. Now you have your samples, you can return them to the lab for analysis. To summarize, grab sampling is cost-effective, quick, and does not require extensive training or specialized equipment. However, samples may not be as representative across all timescales. Automatic sampling allows for more continuous monitoring and is good for detecting peaks of pollution. However, it requires specialized equipment, which can be costly and requires training. Passive sampling allows for continuous monitoring in the environment, but only gives you an average concentration over the sampling time period.